now what we do is that we will simulate this monostable multivibrator and see whether we are getting the same pulses that whatever we have seen. So, for simulation, let me see the circuit. This is a circuit that we require. So, one thing is that I require one op amp. So, I will take 5 terminal op amp here, connecting in the same fashion what we have seen there, or you can also swap. Then I need one diode, and I also need one capacitor, one more resistor which is R1, then I need R3 and R4 too, right. I also need a ground, I am taking a ground. Then I need a power supplies, I will go with sources and DC voltage. So, this particular block should be connected with plus VCC, and we are using 15 volts. So, I am changing it to 15 volts. We have used TL074 for this. If you do not have TL074, you can also go with the 741, but TL084 is a quad op amp, or TL074 or LM358, anything. Then we also need another power supply for the negative minus VCC. So, V1 corresponds to plus VCC, V2 corresponds to minus VCC, and the ground again connected to ground, the positive terminal. So, everything should be a common ground in this case. Output of operational amplifier has to connected to R3 resistor, and other terminal of R3 resistor should be connected to R4, and other terminal of R4 should be grounded, but the values of R3 should be 10K and R4 should be 4.7K. The positive terminal should be connected here. So, slightly moving it down, I am connecting it here, and the diode should also be connected here. Then the other terminal should be ground. This is ground. Okay. So, this particular part is done. Then we need one resistor which is of 3.3K, 3.3 kilo ohms resistor as a feedback resistor, which decides the charging time of our capacitor, and the value of C1 for our design requirement is 0.22 microfarad. So, all set. Now, just before providing a triggering circuit, my plan is to just have a look. So, I just gave two sources two scopes, one is at 2 probes, one is at negative terminal, other one is at output voltage. Let me design triggering part 2. So, I will take capacitor which is of 10 nanofarad, then I go with pot rather than this. I will take potentiometer and connecting from here to here, and I also need a diode. So, I am taking a diode. Right. So, before connecting the output this particular terminal to positive terminal, let me check whether it is giving me the spikes or not for our required value. So, in order to test it, what I will do is that I will take a function generator, which is nothing but in this case clock voltage. So, I need a negative triggering. So, I am reversing the voltage. So, what we have also seen in the previously, I just reversed it. I will take a ground, connect at the positive terminal. This is what even we have done. This voltage I am connecting it here because right now I am not interested at this portion. Let me check it here, and PR2 the probe will be connected at this point, and one more probe should be connected at this point. But since it is floating, you cannot see anything. So, what I will be taking is I will take one more resistor, but the resistance value should be little higher enough, otherwise it may load. So, I will go with it is good to go with always higher resistance value, so that it will not draw much current. So, it will not load the system too. So, right now the circuit is done. So, what I will do is that I will select this circuit part, I will keep it aside. Let me select this, then keep it aside. Now, the intention was to check this. Let me check this particular first, right. Now, before running, we need to also set the same settings what we have get from the encoder, so that it shows this particular portion shows the signal that we are receiving from the encoder. So, we are also getting a clock voltage of 5, yes, since we have reversed the terminals here, which means that we will get a -5 here when there is a positive 5 here. If it is 0, it will be 0. Then the frequency, the maximum frequency we got somewhere around 1.5, that we have seen in the Excel, or we can go with whatever we have recorded values. So, if you see at this point 0.43 and 0.2, 1.58. So, I will go with 1.5 K just for an understanding right now, 1.5 K. And here it is clearly indicated that the on time and off time in this case is not fixed, right. So, I will go with 1.5 K and on time as 430, okay, 1.587, 1.5873 kilo. Now, when we calculate the the duty cycle, because we have to give only input as duty cycle. So, on time by total time is the duty cycle, 0.43 divided by 0.63. So, 70, approximately of 70% duty cycle. Even when you reverse it, it remains the same. So, the duty cycle should be 70. So, what I will do is that I will go here, change it to 70. So, that is the reason we are designing a monostable multivibrator. The reason is that when we look into the signal, it is clear that no matter what, your on time as well as off time is always fluctuating with respect to time. So, if I directly integrate the output of the encoder without using a monostable multivibrator, it is very difficult to analyze. You may get an analog output voltage, but it is very difficult to correlate with respect to the RPM, because the on time as well as off time is keep on varying. What if we make it, what if we fix at any one particular value? If we can fix one value and integrate it, since the value on time is constant throughout the operation, or one particular value is constant throughout the operation, if the motor is rotating at a very higher RPM, the number of the constant pulses will also be higher. As a result, on an average, the area under curve, if you see, we can see the more amount of area of on time we can observe. As a result, if you integrate that particular signal, which gives you the varying voltage. So, with that intention, we have used a monostable multivibrator. Let us see whether it will work or not. Now, let me run, keep it split. Okay. So, fixing it looks good, but difficult to understand. So, go to grapher directly. Okay, one by one we will see. So, PR1 corresponds to the input, PR2 corresponds to the differentiator output C and R, and PR3 blue color this is sky blue and this is blue. Blue color indicates about output. So when I go to the graph, so I'll first enable PR1, disabling PR2 and PR3. It is clear we are getting on time as well as off time, on time as well as an off time, similar to the previous one, but since you have a shift, you have this too, right. Then when you see PR2, right, the pulse width is little higher, but during the negative cycle if you see, because we require only the negative pulses, it is good to go. Then when you only see the PR3, you are getting only the negative pulses. So one thing is clear that this particular circuit is giving me the negative pulses. Now what I will do, I will connect this at this point, because it is giving me the negative pulse right now. So I will connect this circuit. So let me shift a little bit here. Okay. So I am just removing the probes, and now I do not need this resistor because we already have R4 here. That is just for our visualization purpose we have connected. I am connecting to this. So replace with 5K. So I will take 2 probes, sorry, one at this point, other one at this point. When I look into the characteristics of the diode, if you see the potential, the junction potential is showing as 1 volt. Let me change it to 0.7 volt, which is realistic to 4007. Now the required time for the capacitor maximum voltage will only go to 0.7 volt. Here we can see. Okay. So the idea was not even that, we have to see the pulses whether it is proper or not. So let me close PR3 schematic. Grapher, then zoom all. So one thing it is clear that at this point I am getting a negative spike, this point I will get a positive spike. Whenever I have a negative spike, the capacitor is started discharging. So that is why, since the capacitors, because of the negative spike, the output of an operational amplifier will go from plus VCC state to minus VCC state. So plus VCC in this case is 15, minus VCC is minus 15. So it will start discharging from plus 15 from 0.7 volt to minus beta VCC. So the time it takes for the capacitor to go from 0.7 volt to minus beta VCC will be the designed RNC value, RC into log 1 plus R2 by R1, in this case R3 by R4. So which we have seen at this point, R4 by R3, right. So this time duration, when if we observed, it was somewhere around 280 microsecond. Let us see whether we are getting 280 microsecond. Let me create a cursor for PR2 and it should be x axis cursor. So we are getting somewhere around 330 micro. So there will be always a, this is a simulated value. The reason is because of the diode characteristics that we have considered, also so many other parameters, the tolerances, everything. Then when you see the complete pulse value, this value is 666 0.89 microsecond. It is almost close to what we have required, which should be less than 620, but it's supposed to be 515.96. But one thing it is clear that no matter what, our signal, the complete signal time duration is not deviating, right. So wherever I have a negative spike, I am getting a on time everything, and we also have enough room for the capacitor to charge to 0.7. So there are no chances of missing the signal. But what if the time duration is higher? What I mean to say is that, for example, say I will go R1 with 5K, just for our understanding what will be the effect of it. When you look into the graph, observe this. So green represents our encoder pulses, sky blue represents our output. So whenever I have a negative pulse, I got on time. But if you observe, since I don't have enough room for the capacitor to discharge, right, it is not able to detect the negative signal from the encoder pulse, and it is again becoming low only when the next sequence is getting. So as a result, over for 5 or 6 signals we are losing 2 or 3 peaks. So the accuracy of the system is decreasing. This is because of design constraint for not properly choosing our charging and discharging rate of your capacitor. That entirely depends upon our R1 and C1 resistance and capacitance that we have chosen in the design. So we have followed all the requirements that is required. We have already looked into all the cases. We have optimized the resistance and capacitance value, and we have chosen 3.3 and 22 microfarad, 0.22 microfarad, right. So in our case, we are not missing anything. This part is clear to us. So let me keep it aside. Right. So we will change different frequencies now, starting from whatever we have recorded, 227 hertz. So one will keep it at 227 hertz. So the duty cycle is also 30% for everything. On time should be higher, so it should be 70% for everything. Okay, let me run. Right now, so since the charging, since the our time duration is smaller, so in this case there won't be any problem, because we are operating at very low frequency. When you inverse it, which is time, we have enough room for the capacitor charging and discharging. Now when we see, even in this case, whenever I have a negative trigger, I have a pulse till I get to the next negative trigger, because in this case we will get a positive trigger, in this case I will get a negative trigger. So this will not be considered, and only during the negative trigger I am getting fixed duration of this on time, then off on time. So there are no missing of signals. Then we will see for another value, which is 357. So I will change it to 357 and let me run the value. Right. Even in this case, all the signals are there, no missing of any pulse. Then I will go with the 515. I will change the frequency to 515 because the voltage is fixed. So that is why I am not changing the voltage. So one thing is clear, that no matter what, since it is a monostable multivibrator, it will always have a fixed on time and fixed off time, and the on time entirely depends upon the next triggering pulse that we require, right. So because of that reason, we have chosen this particular the resistance and capacitance value. Not only that, please be careful when we are giving a signal at the triggering input. Any changes will ultimately affect the output results. So this should be always a negative triggering pulse. So now I hope it is clear why we are doing it. So, the next part, so since if you observe here we are getting a negative, so if you observe here we are getting on time the T1 duration, fixed duration during the negative pulse, and the stable state, this is unstable state, this is a stable state, the stable state is in positive, but we require in a ulta way. So, what we are doing is, if I integrate and then pass to an integrator, so that we will get a signal. Right now we have the output from this is this way. Right. When I pass through this, I will get a signal. So, this will be minus 15, this will be plus 15, right now this is minus 15, plus 15, and this is minus 15. So, that I will be integrating this. So, depends upon RPM per depends on the RPM per second, the number of pulses that we are getting will be always varying, but since it is a fixed duration, when you integrate it, the area will be keep on increasing based upon the increasing RPM. As a result, we can see the linear. So, in the next class we will see the simulation of this as well as simulation of this. Once everything is done, we will integrate it together and changing the RPM, changing the encoder frequency at this point with these frequencies, changing these frequencies, we will observe what is an integrator output we are getting it. Okay. Till then, take care.